Hello, this is Prof. Nanius. Um, the purpose of today's video is to say a few words about um, some theorems considering first order differential equations, some theorems concerning, I should say. And I want to talk about the uniqueness theorem, which means if there's a solution that satisfies an initial condition, is it unique? And the existence theorem, meaning if you have this differential equation, are you guaranteed to even have at least one solution? And I'll just say this up front. If you're not in my differential equations class, if you're looking for a presentation that provides rigorous proofs, this is not it. This is going to be highly informal and geared toward somebody who has not had real analysis and has not studied the convergence of series of functions. And in other words, if you know what equicontinuous means, if you know what compact means, if you know what uniform continuity means, this video is not for you. So let's get started. And we'll start off with this right here. And this is the idea. We're interested in existence and uniqueness theorems for first-order differential equations. Meaning, for example, if you have y prime equals f of xy, and you're given an initial condition, in other words, at a point x naught, you have y naught. For example, this is the kind of thing we're talking about. Suppose you have, let's say, y prime, oops, not sure what happened here, is equal to xy with y of 0 equaling 1. That would be an example. Or you might have y prime equals, let's say, x squared, y to the 2/3. And maybe you might have y of 0 equaling 0. So the question is, for these sorts of differential equations, can you see if they have a solution at all? In both cases, the answer is going to be yes, but we'll see why. And the second question is, if so, is it unique? Now, what we said is stated in class. We stated this the following way. Imagine this point x naught, y naught. In other words, if you input x naught into the hypothetical function y, you get the y value y naught. These points you can plot in the Cartesian plane. So let's just draw a hypothetical Cartesian plane. And here's your point x naught and y naught. This is a little too sensitive or something. I should erase that and make it a little bit more readable. But you have this point right here. And remember what this thing here does. This y prime equals f of xy. Remember, y prime, remember, is dy dx. And this gives a slope. I'm not sure what's going on. Of the line tangent to a function y of x. So you learn that in Calc 1. And you probably also learned that you could probably plot these things like these little, here you have f of xy, they call it g, equals xy. And what they're doing here is what they're saying here is that the derivative, y prime, is equal to the product of x and y. And since the derivative gives you a slope, they're drawing little segments of that slope. And the idea here is if there's a solution, that means there's going to be a function whose curve follows these tangents perfectly. So that's what this existence means. Is there such a curve? Uniqueness means, is there only one? So here's the theorem that we stated in class. If f of xy equals y prime, and there is a rectangle R, and we have x naught, the starting x point between B and A, and y naught between some things C and D. So this is the idea. Your rectangle here looks like this. This is x is A. This is x is B. This is y is C. And this is y is D. And this is a strict inequality, so your x, the points in the interior of this rectangle. And f of xy as a two-variable function is continuous on this rectangle R, then there is at least one solution. Y, where y of x naught is y naught. So in other words, there's going to be at least one function whose graph runs through this initial point, let's say this one, and follows these little slope lines perfectly. That is, if you take the derivative of the function of y, you'll get this product right here. So that part is the existence part. Now here's the uniqueness. If, in addition, we take the partial of f with respect to y is continuous on R, then the solution is unique. Now you can say a little bit more. You can say the solution is valid so long as the solution curve stays in the rectangle. Now, if it starts to leave the rectangle, then all bets are off. But you know there's going to be one solution that works inside here. Now, we stated that in class. So the question is, how are such assertions proved? Now, the thing I'm going to use, the first proof, the existence, I'm going to use a lovely little proof that's found in this book right here, Petrosky, Ordinary Differential Equations. The proof of this, again, these are little Dover books. They don't cost much. Some of them are even have online versions. And the theorem is proved in chapter 3. I'm going to give a little sketch of it. Rigorous details require the kind of detail you normally receive in a real analysis class or advanced calculus class. But the reason I'm going to go through the proof, I'm not going to go through the proof in detail. I'm going to sketch out a hand-wavy version of the proof and tell you what things you need to fill in. So this is the idea. Start with your rectangle R, and here's your point x naught yy. Now notice f of xy is continuous. And y prime, the slope of the hypothetical solution, is equal to that. So what this means, and you learned this in Calculus 3, What it means is that there is some number m where m is greater than or equal to the absolute value of f of xy, which is equal to the absolute value of the derivative, which is the slope on r. Now, if you've had some real analysis, the keywords and tricky phrases here is the continuous image of a compact set is compact. And so, or closed and bounded in a metric space. And this is what's going on here. Now, what this means, this is a slope. So this means that the little slope lines, or those little segments that we talk about here, because remember, those are the y primes. Y primes are equal to the slope of this. That means they're only so steep. They can't get any steeper. That's going to be important for us here. So what happens is, if you have that, you can start by drawing a line of slope m through this point, draw another line of slope m, slope negative m, like so. And it may intersect the rectangle here, or if your rectangle is like that, it might intersect it at the ends. But it intersects the ends of the rectangle somewhere. Okay? Now, start at x naught, y naught, draw a line, draw a segment, a small segment of slope f x naught, y naught. Now, because that slope is going to be less than or equal to m, that means the slope, let's go in the positive direction first. It's going to look something like this. You can't exceed this because remember, m is a maximum bound. So you draw this little segment here. Okay? Now at this point is also in the rectangle. The f of xy evaluated this point, which gives you a slope, can be at most equal to m or a little bit less. It can't go up like this. Has to go up shallower. So it goes up something like that, or maybe it goes down. This point, you have a new point. You throw that in, f of xy. Maybe it's negative, maybe it's something else, but it can't, in terms of steepness, it can't be more steep than that or more steep than that. So it's going to stay in your rectangle. You have another point and so forth. And you just build a little line segments. At each point, the slope of the line segment is less than m, so it has to stay in this triangle. It can't get so steep it leaves it. So it has to stay in this little triangle here until you run out. So let's just stay in there up to here, wherever that is. So now this little piecewise segments, we can do something similar in the negative direction. And let's stop at some point. Let's stop here. So let's stop there. So you have this piecewise linear bunch of line segments. Each segment, its slope is given by the formula f of xy, but it can't be any greater than m or less than negative m. So we have something that looks like that. Now call this thing, let's call it phi1. It's a function. How you know it's a function is because the slope can never get so great that the function, the line segment turns on itself. Because it can't leave this little area here because of the bound of the slope. So this is a function. And the slope equals this thing here at let's say at n1 points. Doesn't matter what n1 is. Okay, so that's a piecewise line segment. Next thing you do is you subdivide. You subdivide this segment here into smaller segments, and then what you do, you go halfway and build a new piecewise segment. So we do this again with smaller segments. Let's say it has n2 segments, where n2 is strictly greater than n1. In fact, you could, for example, do it in an organized fashion where you use double the segments every time. And you get another piecewise linear function, too. So now you have more segments. And then repeat this process an infinite number of times. So we could, for example, since we have the choice of the number of segments we use, we can say n2 is equal to 2n1 and so on. n3 is equal to 2n2, etc. And then do this again for 3, so and so forth. So each one of these will be a function, and the graph is a bunch of segments. Here, these segments are shorter than these segments. The segments in phi3 is greater than twice as many segments as in phi2. This uses twice as many as this. So you have a bunch of little segments here. And you repeat this process in the other direction too. So if you do this an infinite number of times, what you get each function, the graph is a bunch of segments. Each one having twice as many, and at the endpoints of each segment, the differential equation, let's call it x, k, y, k, is equal to the slope there at the endpoint. So basically, the first one right here, these functions, the differential equation works for these points. The second one, the differential equation is satisfied for twice as many points. Then the next one, the differential equation is satisfied for twice as many points as well. And so what you're really doing is you're building, and I'll try to draw this a little bit better. This will be your first approximation. Your second approximation only goes half as far. For each segment. Your third one, a little bit more. And you can see these things they're straight segments, but they're getting closer and closer to a curvy line. Now remember, the slopes of the segments in any of these is bounded by plus or minus that number m. So each segment, the slope can be only so steep in either direction. Now, here's where the hand waving occurs. By real analysis. What you can show is this family of functions here, which each one is continuous. This forms what's known as an equicontinuous. And what that means is that each one of those things is continuous, right? And remember, you heard about delta epsilon, Calc 1? Like for every epsilon, there's a delta such that if 2 points are delta close, then the f of those 2 points will be epsilon close. Well, what this means for equicontinuous means that for this entire family, if you at any point of the domain of any of these functions in the family, if you give an epsilon that you tolerance you want to meet in the range, the same delta will work in the domain no matter which one of these functions you choose. Now you have to prove that, and I haven't proved that, and I won't prove that here. It's proved in the reference I gave. I will not be proving it, but you can probably guess, because remember when you did those epsilon delta proofs in Calc 1, and if you had a line of slope m, little m, remember that if you're given epsilon, the delta was always epsilon over m. Well, remember, each one of these, the slope is bounded by capital M. So your delta that you're going to use will be analogous to epsilon over capital M for any of these, because the slopes of each segment are bounded by this. Now, if you didn't understand delta epsilon in Calc 1, this will be complete gibberish to you, but that's what happens. Now, since these have this, that means that there is some subsequence of these. I'll call it a subcollection that converges, meaning gets close to a that. And you also need to show that for the thing this converges to, that it has a derivative, and that the derivative meets this condition here. Now, I didn't show that. It's shown in here, but if you want to try your hand at that, it's one of those, you compare the difference quotient to what you want, and you use something analogous to the triangle inequality to show that uh, those things can be made arbitrarily close to each other. Now, the reason I went through putting these little line segments, is that if you need to solve a differential equation numerically, the formal method is called the Euler's method. And you can program it. And the programming is you basically, you input your start point, compute your first slope, y1 prime equal f of x naught, y naught. And then you input this, you take your step size, here's your delta x, here's your beginning point, and you want to figure out what this new point is. So your new y will be your old x plus the slope, which is this, times delta x. And that gives you a new point. And then you repeat the process. And then what you can do, what we're doing in our proof is that what we're doing is we're making delta x smaller each time. So you do this one time, you get an approximation. Then you do it again with your new delta x is the old delta x over 2. Then it's the old new delta x is the old delta x over 4, and et cetera, et cetera, et cetera. So that's how you can do this numerically. Now, this is existence, does not guarantee uniqueness. What about uniqueness? Well, remember uniqueness, you need the partial of f with respect to y to be continuous. Well, we need it to be bounded, really. That's what the proof actually uses, and you get boundedness if that's continuous. And I'm using this reference here, wonderful reference called Coddington. And I'm not going to actually give you the details of why the procedure works, but I'll show you what the procedure is. So the first thing you do is you start off with the differential equation itself. And then what you do is you integrate both sides with respect to x. And you start at the starting point and you go to some hypothetical. So let's use dt here. And we're going to use t instead of x because we're going to use this as our variable. Now, this integral from the fundamental theorem of calculus, you're integrating the derivative, so you get y of x, what is y naught, is equal to this integral here. And then add a y naught to both sides, and you get this so-called integral equation. So what I've done is I turned this differential equation into an equivalent integral equation. Now, to be rigorous about this, you'd also have to start with this and show that you can get that. You can do that by just differentiating both sides. I don't want to waste your time doing it, but the proof is in Coddington that works the other way. So anyway, this is what we want to get to. So we want to find a sequence of functions for which this works. So now let's start off with a base function. Let's say phi 0, and that will be the constant function y naught. So now let's form phi 1 will equal y naught plus the integral from 0 to x of f of t y naught, or which is phi 0. Now this is a function that only involves t and a constant, so it can be integrated. Then we form a new function by stating the same this, but now we're going to integrate f of t. Now we're going to integrate this new function that we just created. So this gives a new dt. This gives a new phi 2 of x. And you keep repeating this process. You do this again. So in the nth step, this is f of t. This will be the nth minus 1 function. And you keep doing this. And what you actually have, so what you do is you obtain a sequence of functions, and I'll give you a concrete example so you can see it in action. N plus 1. So what you'd actually have to prove, and I'm not going to prove this to you here, but the first thing you want to prove is that, one, these in the limit as I goes to infinity converges to a function. And that differentiable function, this works if you have that bounded. And the reason this is that the t is going to be bounded here. You need this to be bounded in the second variable, though, because you don't want this to swing too far away. So the first thing is you have to show that this converges to something. And the second thing you have to show is that what this converges to satisfies this. It's that the derivative of it, you have to show the derivative would exist, and it exists for all of these. And you'd have to show that it meets, I'm sorry, that it meets this condition here. That I misspoke here. But yeah, you have to show that it meets that. And I'm not going to show either of these. Both of these are shown in this book here. It requires knowing how to prove things, and it requires some advanced calculus. But let's look at an example of what this might look like. So let's start off with a function f of xy, and this is in Coddington. Let's start off with this, and let's start off with the initial condition. Y of 0 is 1. Okay? So your very first function would be y naught, which is 1, plus the integral from 0 to x of f of t 1. Because remember, this is a y0. Well, remember, this says multiply the two things. So you're integrating with respect to t. And it's not hard to see that this becomes 1 plus t squared over 2. Evaluate between 0 and x. 1 plus x squared over 2. That's going to be your first function. Now let's do the second one so we can get the hang of it. The second one, we'll start off with a y naught. And it's going to be f of t 1 plus t squared over 2. Now remember what f says to do. F here says multiply the two together. So this is t multiplied by that, so it's going to be the integral of t plus t cubed over 2, right? That's what it means, is you multiply t, this times both of these, and that's not hard. The integral is going to be t squared over 2 plus t to the fourth over 8, value between 0 and x. And that's going to be 1 plus x squared over 2 plus x to the fourth over 8. Let's do one more. So this is going to be your second one. Your third one, 1 plus 0x, f of t, 1 plus t squared over 2 plus t to the fourth over 8. But remember, f says to multiply this. So it's going to be t plus t cubed over 2 plus t to the fifth over 8 dt. So you integrate that. Your third one is 1 plus integral t squared over 2. Well, it's going to be x squared over 2 after you put in the x. That's going to be x squared over 8. That means x to the fourth over 8. And this is going to be x to the 6 over 6 times 8, etc. Now, if you're wondering, and so notice you keep getting this series here. It's a series, right? Now note, this is what's kind of interesting. Note the original equation right here, xy. It turns out that if you have y prime equal xy, you can show that y equals x e to the x squared over 2 is a solution. When x is 0, y is 1, right? And you can do that. So if you take the derivative, of this, well, chain rule, 2x divided by 2 is x e to x squared over 2, which is xy. So that checks. And then if you take the Taylor series of this, remember the Taylor series of e to the whatever is 1 plus whatever squared over 2 factorial plus whatever cubed over 3 factorial, etc. Well, if you plug this in, We plug in x squared over 2. Well, if you take that and square it, that's x to the 4th over 4 divided by 2. This here, it's x to the 6th over 8. 8 times 6 is 48, etc. So what we're really doing when we're doing this process, we're actually getting the Taylor series of this evaluated at x equals 0. And that's how this method of successive approximations, that's what it's called, by Picard. So that's what this is called, the Picard successive approximation method. And so this, again, the details is in this wonderful book, and I know for sure that there's a PDF copy you can buy because I have one. But anyway, that's how these things work. I'm not going to hold you responsible for them. And thanks for watching.